In this project, we worked with a Lego Spike Prime kit, specifically in the activity Playing with Objects, where the main objective is to design and program an automated system capable of interacting with objects, in this case detecting and manipulating them. First, we assembled the robot by following the robot guide. The system mainly consists of a mobile base, a motor that acts as an actuator to move the mechanism, and a sensor that allows the robot to detect the presence of an object. The process works as follows. Initially, the robot remains in a standby state until the sensor detects an object. Once the object is detected, the actuator is activated and performs a specific action, such as pushing, grabbing, or moving the object. After completing the action, the system returns to its initial state, ready to repeat the process. This allows the robot to operate in a cyclical and automated way.
Now I will explain in a simple way how the code of a Lego robot works. First, the program imports some libraries that help us control the motors, the distance sensor, and the sounds. Then we set the ports where each component is connected. After that, the robot starts by moving the arm to an initial position, and it makes a sound in 2 different times to show that it is ready to develop the actions contained in the code. Then the robot moves forward. In the code, there is a condition that makes the robot continue moving until the sensor detects an object at a certain distance. When this happens, the robot stops automatically, lowers the arm to interact with the object, and makes sounds again. Finally, the robot moves backward to return to its initial position. It is important to say that we made some changes to the original code, like detection, distance, the speed, and the backward movement, to make the system more precise. In general, the robot follows a simple sequence: move, detect, act, and return.
I will explain how we calibrate the sensor and the actuator in the system. First, for the distance sensor, we did many tests to see at what value the robot works correctly. In the code, we use a value of 100 mm. That means the robot detects an object when it's closer than distance. We test by moving the object closer than the sensor and watching when it's works better. This is important because if the value is too big, the robot reacts too early, and if it's too small, it may not detect the object. So, for the actuator, we test the motor of the arm. We adjust the movement angles and time first. We made small movements to position the arm, and the another movements so the arm goes down completely to touch the object. We also adjust the motor speeds. If it moves too fast, it's not precise. If it moves so slowly, it takes more time. We also adjust the backward movement of the robot so it can return to the correct position. In general, calibration was very important to make the system work correctly every time.
During the practice, there were difficulties arose both in the assembly and in the operation of the robot. First, during the Lego assembly, some pieces were not completely firm or properly aligned, which affected the robot's stability during movement. We also experienced issues with the calibration of the distance sensor, as in some cases it didn't consistently detect the object. This was resolved by adjusting the detection range through multiple tests. Another difficulty was the adjustment of the actuator, specifically the arm, since initially it didn't lower correctly or did so with excessive force. These were corrected by modifying the motor's angle and speed. Additionally, at certain moments the robot moved backward unintentionally because the sensor incorrectly detected another pieces. To fix this, the movement parameters were adjusted. Overall, all these difficulties were resolved through trial and error, achieving a more stable system performance.
As a conclusion, this project allowed us to understand in a practical way how a basic automated system works by integrating sensors, actuators, and programming into a functional process. We learned the importance of calibration, since small adjustments in the sensor and motor can significantly affect the system performance. Through testing, we were able to improve detection, movement, and overall accuracy. We also understood how to structure a program based on a logical sequence: move, detect, act, and return, allowing the robot to operate in a continuous cycle. Additionally, trial and error was key to solving issues related to assembly, detection, and actuator movement, leading to a more stable system. Overall, this experience helped us understand how hardware and software work together and how small improvements can enhance system performance.